This conference will now be recorded.
Do you have any doubt regarding RNA stability study? Harshit,
Huh.
what exactly we do in RNA stability study according to the RNA theory?
We raise the temperature so that the time needed will be decreased.
Time needed for what is reduced? Hello? Why you need to increase the temperature, Preethi? You need to answer. Ashita?
Ma'am, I was absent to yesterday's class.
It's a very basic concept there, so you cannot give that reason because you already studied in UG also. So anyway, let's move ahead. We were discussing about the stability study. We understood about the kinetics, first order kinetics, zero order kinetics, and the pseudo first order kinetics also, and also a little bit about the second order kinetics. Means degradation of the drug can happen in any of the, you can follow any of the kinetics. We should have a suitable methodology, experimental methodology to determine the stability. That is nothing but the degradation of the drug happening. So when we talk about methodology, we should also have a suitable analytical technique also to find out the changes happening in the during the degradation process. It can be changes happening with respect to physical property or the chemical, and most of the time it is the physical property which get changed. Fine. So visual changes are very rarely which happens like color change, but still we can have a methodology to determine the visual changes also like color change, finding out the intensity of the color change. So the RNA stability study mainly emphasize on the influence of the temperature. In the sense, we are trying to accelerate the degradation process so that we get the information at the earliest and helps us to come out with some conclusion out of that result. So those drugs undergo degradation at the different temperature. We need to carry out the degradation at the different temperatures. Fine. Other than the room temperature, we need to carry out and plot the graph between log K and 1 by T. So this is according to the straight line equation which we got understood about yesterday's, that is Arrhenius straight line equation. This is what? This is a basic equation, and this equation is practically you are going to apply it to determine the Arrhenius constant, that is the delta EA value. That is most important. That is activation energy. Heat of activation is called as EA. So we need to carry out the experiment at a different temperature, determine the K value, plot it on the y-axis, and the x-axis you plot 1 by T value, and you take the slope out of it, you get the EA value. So why the EA value is so important for us is because that if the drug is affected by change in the temperature, say for example, if your drug is not getting changed at the 60-degree or the 70-degree, means it doesn't, we cannot carry out the accelerated study using the temperature concept. That is, you cannot apply Arrhenius concept. So that is understood based on the EA value. That's what I was telling you yesterday. We need to have, means to carry out the accelerated stability study based on the Arrhenius concept. We need to have the information about the EA value so that we can decide whether I can use that is stability procedure or not. Because if it is not affected by change in the elevated temperature, that is accelerated temperature, then we cannot get any information out of it. So suitably, the range should be between the 10 to 30 kilocalories. So any degradation which happens in the presence of change in the temperature, which has an EA value between the range of 10 to 30 kilocalories per mole, those are the degradation which are dependent on the temperature, can be conveniently, we can understand its stability aspect by increasing the temperature to the highest side. So also, we should also know a little bit about the limitations of the Arrhenius theory. I already made you understood that what one of the limitations, that means all the degradation cannot be analyzed based on the Arrhenius concept because it is mainly the one which happens in the presence of the temperature only. Fine, that is the in general limitation. but there are specific limitations. Though the degradation might happen by increasing the temperature, there are some limitations which can be considered, which need to be considered. So higher temperature, there is a possibility of solvent evaporation. Okay, and what happens because of this solvent evaporation, there is a chance that the moisture is lost. Okay, and there will be imbalance in the moisture content present in the material, because the why the moisture we are talking here, because moisture also plays a very important role in the degradation process. If we are losing that moisture, so whatever the results we get by increasing the temperature, it's may not be the true picture. So that's the one limitation. The second one is higher temperature. I think I told yesterday also. There is a possibility that you might lose the original form of the drug molecule itself. So higher temperature, there is a less humidity. That's one more thing, and oxygen solubility is also less, thus hindering the predictability of the room temperature stability. So what happens many of the time we lose that realistic situations because of the elevated temperature. So in the elevated temperature, no doubt the humidity will be very less, and the oxygen solubility also will be less. See why these two are important. Generally, we store our drug in the normal room temperature, the normal storage conditions. So in the normal storage conditions, the temperature is room temperature is 37 to 45 degrees centigrade, and also the presence of oxygen will be there. Fine. So the influence of this oxygen and the humidity is missing when you carry out the isolated stability study. So that is another drawback. Means though we get the result, we could get some idea about the degradation aspect, but we are losing the original basic things which is happening at the room temperature. We are not able to predict exactly its stability at the room temperature because of the absence of the moisture and the oxygen, especially those drugs which are sensitive to the moisture and oxygen. We have to be carefully plan our experiment. So we may not able to do this applying the Arrhenius concept. Maybe some other method we have to go with. The next one is the viscosity decrease. This is the change in the physical property of the preparation itself, because there is a direct relation between the temperature and viscosity. In the sense, as the temperature increases, viscosity decreases. So it is going to alter the physical characteristics. So again, that can add up to an error, the result whatever we get out of it. And again, there's a different degradation mechanism which may predominate at different temperatures. There's one more thing. Though we in simple way we are telling the degradation of the drug every time, this degradation have different pathways. We are actually not concentrating much on that. There's a different chemical reaction ultimately. So this can the chemical reaction pathways may be the different types. It may follow one pathway at one temperature, another pathway at the higher temperature. So that also becomes problem for us to interpret. Means there are limitations with RNA stability studies, but keeping in mind what are those limitations, we can always plan the experiment to carry out the isolated stability study. But one thing, it should fit the criteria, required criteria is its EA value should be within the range of 10 to 20. If the EA range is between 10 to 30, sorry, so then that is an ideal candidate for understanding its degradation process. And still, if it is, even though it is having the EA value of the required range, then what are the other things which can limit its applications are, these are the points. This, even then also there are limitations associated with this. So that's about the RNA stability study. So fine. So this is just a graphical representation of the data. Now we understood about the RNA stability study, different temperature we need to carry out. Okay, fine. Then take the K value, plot that K value against the 1 by T value. All that is fine. But let us see how it can be practically used for our purpose. Okay, especially with the pharmaceutical dosage forms. So when we plot, for example, we have a drug A, we have carried out its stability study at a different temperature. Hope the graph is clear for you guys. So this temperatures, whatever you're seeing in the different color lines, they are the different lines with respect to different temperature. So we are ready with this line. That's what the first step in the RNA stability study. Different temperature we need to carry out, plot the graph, take out the slope value, all that is fine. Now this graph again I can use it for the different reasons also. I mark out the point 90%, how much time it takes for the drug to degrade 90%. So what I will do now with this different lines is I just extrapolate this line such that I'll identify the point, that is 90% degradation, which happens at the 40°, 50°, 60°, 70° and 90°. So I got an idea now, right? For the drug to get degrade to 90%, fine, that is reduced from 100% to 90%. In the sense, don't think the other way, 90% drug is getting degraded. So it is 90% is still remaining, fine. So 90% potency has come down 100 to 90%. So 10% is gone. So you are marking out that 10% on, that is 90% on the line. So take out those points, fine. So 90% potency, now note down the time in the x-axis, number of days in the x-axis. Plot another graph having this value in the y-axis. Take out this data, whatever you would have got after extrapolation. You plot it separately in other graph in the y-axis like this. Log of days to 90% potency. Means the time taken for the drug to reduce its potency from 100% to 90%. So this value would have got it from the first graph and plot against 1/t. So now what is the benefit of this graph is, now I can back extrapolate the line towards the upper side, because 30° centigrade stability study we have not done. We have done only from 40 to 90. Sometimes we don't even do at the 40 also, we do it from 50 to 90° centigrade. So what I can do, the advantage of this graph is what? One second. So I can now extrapolate the line backwards in this direction. Though I have not done the experiment at the room temperature, the excited conditions whichever I would have used for calculating the 90% potency, I extrapolated. Now it is an advantage for me now, because I can extrapolate this line back to the x-axis to understand this potency. The log number of days to get the 90. This is the time actually. This y-axis is the time. That is nothing but the day. I can tell it as a time in days, because degradation not happen in 1 or 2 hours, like 1 or 2 minutes. It happens in the days also. So what I do is, now I extrapolate this 40° point to y-axis to get the what is the time taken for the drug to reduce from 100% to 90%. Same when I store it at 30°, what is the time taken for the drug to reduce from 100% to 90% potency. So this is how you are supposed to calculate the, one second. Hope you understood about the application of the data, what we get out of the RNAs experiment, that is accelerated stability study. So ultimately, we are actually trying to determine the stability of the dosage form, which we are planning to understand its shelf life. So in order to get that shelf life of any drug at room temperature, that is most important. We never store our drug formulation in the accelerated conditions. The accelerated conditions are applied only to fasten the reaction, so that we get the information at the earliest, which helps us to decide about the stability condition of the drug at the room temperature. So the data, whatever we get from Harinius study, okay, and that is the first graph is the data which we get it from Harinius stability study, and that data can be utilized however we want. The one application is this one, just right now whatever I completed. The another application is, previously I told you, helps us to calculate the EA value. The slope whatever we get out of this graph, we can calculate the EA value, that is activation energy value. So this EA value at this point, if anybody asks you what is this application, as a pharmaceutical person, we may not find much of application for our knowledge, but of course it has a lot of information to tell. But for our purpose, the same data, when I use it for the next graphical representation, then it has a lot of advantage. So that is this one. So I can use the data like however I want to understand the stability of the drug at room temperature. So this is just one example I've given you. The next one is, there is something called as calculation of overage. This based on the pharmacokinetic study or the toxicological study, all that initial trials, they would have come out with the dosage form. That is dose required for the therapeutic action. 100 mg, 200 mg, 500 mg, whatever we so confidently use it for the treatment purpose. No? So that dose you would have calculated based on the extensive studies. Okay, but what happens? This dose, whatever you would have calculated, like 500 mg, for example, when we formulate it, there is a chance that during its storage condition, that drug might reduce because of the degradation. Means the original amount of the drug, right, that 10% of the drug might get degraded. So now 10% of 100 mg is like 90. By the time of its usage, only the 90 mg will be active form. The 10 mg would have lost. So we might avoid this by selecting the suitable storage conditions. But sometimes even after that, there is a chance that the 10% degradation you cannot avoid for different reasons. So what usually they do is they calculate something called as overages. That extra dose, I mean amount. For example, if it is 100 mg, they know, and that is which is active, and they also have an idea that there is a loss of 10 mg during its storage condition, which is inevitable. I mean, which is not avoidable. So what they do is they add extra 10 mg. It is acceptable. So by the time when the patient consumes that in dosage form for any therapeutic purpose, so while consuming it, the 10 mg would have lost, but still that amount which is required for therapeutic action 100 mg is retained. So that's called as overage calculation. So that overage calculation can be done by again plotting the graph. One is the percentage, that is the amount of the drug in the y-axis, fine, and in the x-axis is the time in the days. So what they do is they calculate, they plot the graph, the data, whatever they have got it in the standard time in the x-axis and the amount in the amount in the y-axis and the time in the x-axis. So number of days they would have done at particular temperature. This I'm talking about specific temperature. So they would have had the information how the drug is reducing from 100 mg to 0%, and they have got the number, that is time, carry out the stability study at one particular temperature. Fine, that is the temperature at which usually you try to save and store the formulation. You plot the graph now, time versus, that is the percentage, that is the percentage of the drug which is present in that particular dosage form. So 100% is the label claim. We know that that is the 100%. So what they do is how to calculate the overage. Now they know that there is a 10% loss, so they want to add 10% more. So adding that, how they decided this 10%. Now I'm telling from my side it is 10%. But how they decided it is 10%? This 100% drug, that is 100 mg drug, is degrading by the time of like almost its 50% is getting degraded in 300 days. Okay, that's what they have the initial information. Almost by 300 days, the entire drug is getting, I mean, more than 50% of the drug is getting reduced. That is more than, that is potency is reduced from 100% to 90% or near to 50%. So this information they have. But I want to keep my drug for the longer time, so that is 700 days. I want to make sure that on the 700th day, the drug is stable, means drug is the dose of the drug is still 100 mg, it is remaining. So in order to get that information, what they do is they will first identify the days, number of days at which they want the drug to be stable at 100 degree, that is for the 700 days. They will mark the point which is a parallel point above the original line and extrapolate back towards the y-axis to get the overage. So this point will tell us how much extra drug I am supposed to add to the 100 mg drug, so that on the 700th day, the dose of the drug is still 100 mg. Though there is a loss of 10 mg, though there is a loss of 10 mg which was happening before, even after that, on the 700th day, to have that total amount as 100 mg, they have to add 10%, that is 10 mg extra, so that on the 700th day, even after the degradation, the drug dose remains 100 mg itself. So that is what the calculation they try to do with the overage means. Like this, the stability data, I'm just giving you idea how the stability data are used for our purpose. Okay, we are not understanding this kinetics with respect to any chemical reaction as a chemistry part. We are understanding this with respect to the pharmaceutical dosage form stability. So these are the applications of the kinetic studies what we carry out and how the data is used for understanding the various aspects. So quickly, let's go enter into the factors affecting the degradation process. Fine. So I'm not discussing in detail that each and every factor. So as I told, these are all the basic chapters which you already learned in the QT. Just one second.
Yeah.
Okay, sorry. Uh, so let's discuss quickly about the factors affecting the degradation process. So as I told, I'm not discussing in detail, just giving you an idea what are the different factors even the degradation can be affected by. It can be like presence of the acid-base catalysis also, which we add as a buffering agent to the maintaining the pH of the solution. No, even that added buffer can affect the stability of the drug. So you should be careful about the whether the added buffer has any influence on the degradation process or not. So the next one is the ionic strength. Not only that, the type of the acid-base catalyst what we add as during the pH maintenance, even the ionic strength of the added these agents can also influence the degradation process. The next one is the influence of most important one is effect of pH on the degradations. So we need to understand this because many of the, especially the solution dosage forms, any change in the pH during the storage condition can have bad effect on the stability of the drug. Fine. So they usually what they do is they carry out the degradation process at the different temperature, sorry, pH, like how we carry out the stability and accelerated stability study at the different temperature. Here they carry out the degradation by preparing different pH solutions and then exposing the drug to the different pH solution and then understand the optimum stable pH. So like this, one of the graphical representation you can expect which can happen with respect to the various pH temperatures or pH conditions, and they ultimately find out the pH where the drug is more stable, and that pH environment is maintained throughout its storage conditions. So that's about the pH effect. Same thing. So by chance, if they ask you like 5 marks or the 8 marks question, you can never expect it as a major questions. It can be as a part of the 8 marks question, as a part of or 5 marks question also. So there's a possibility of asking this indirect questions. So just an additional information, I was telling you there are different pathways the drug can follow. So this is how the pathways can be represented. We are not understanding in detail how exactly all this happens. Is to get an idea, the degradation is not a simple thing which happens for any drug molecule, which is affected badly influenced by the various factors: temperature, humidity, even the presence of the added buffering agent, its ionic strength, the pH of the environment in which the drug is exposed. So all this can affect the degradation, and when the degradation is happening, it can happen either just a simple degradation as a one-way direction, or it can happen in the multiple ways, like as you can see here. We can take the different pathways, and every pathway can be of a different rate. So it is more complex overall. So fine. So chemistry aspect we are not bothering to understand in detail. Only our concern is how to identify the degradation. Okay, and we already got an idea like RNA's concept where we can carry out the aggregated stability study. Fine, and some analytical techniques are also important to identify this variation happening. Okay, so some of the examples, if they ask you to mention, examples are ester hydrolysis, which follows the second order kinetics. Okay, which is catalyzed by acid and base. I want you guys to remember some of the examples. So ester hydrolysis is one of the examples which happens with the second order kinetic process. Okay, so during its study, what there is degradation happens either with H plus or the OH. We are trying to maintain it constant. Is kept considerable at the higher concentration. That's why it is called as pseudo persona. I gave you an idea last time also. If the two reactants are taking part in the degradation process by chance in the kinetics, if one of the reactant concentration is always at the higher side, though there is a two reactant, it behaves like a one reactant. So that's why it is called as pseudo first order reaction. So this degradation example for that is ester hydrolysis, acid and base ester hydrolysis. Fine. So they're not going into all that. I just wanted to tell actually there are various things. See, one simple hydrolysis, whatever we are imagining. Okay, we got to know it is zero first order reaction. Fine. But this simple reaction, what we are thinking is affected by change in pH. So they have understood from the experiment that 6 different pathways, the different pathways it follows for during the degradations. So you can imagine the complexity. So if the person who is actually involved in understanding in detail the degradation, chemical aspect, chemical process aspect, he would have understood in detail what are the different 6 pathways. Okay, and each pathway will follow the different order of kinetics. So, but as a pharmaceutical person, we are not actually much bothered about this to understand because, but we should know that there's a complexity involved, and that is again affected by the pH and also added surfactants. Modification can happen because the modification in the chemical structure. So, like this, it goes on. So, salts and esters usually this is not required. Right now, I'm just skipping that. There's one more thing as an example to be remembered is oxidation reduction process, which follows the first order or second order. I'm just giving you idea with example which order of kinetics this degradation can happen. Ester hydrolysis, pseudo first order reaction. Next is oxidation reduction process, which generally follows first order or the second order kinetics. Again, in the oxidation, there are differences. Auto oxidation process which happens. Okay, all that is that in detail. So generally add the antioxidants to overcome that. The next one is photolysis. Already we know it follows the zero order kinetic, but there are even the photolysis process which can happen by the first order and the second order. So ultimately, we should know some of the examples. So it's a photochemical reactions which happens in the presence of the light. And again, that light depends whether it's a direct light or indirect light, in the sense the direct sunlight or the artificial light. All that we already completed just beginning of this chapter. So the kinetic, it generally follows the zero order, and visual change happening is the color change. But there are even photolysis process which can result in some major chemical changes which can follow the first order and the second order kinetics. So it's an example that photolysis uses chlorpromazine hydrochloride is one of the example which undergo photolysis reaction. One second. So, as I told, this is a very vast chapter. We are not learning in detail. Just superficially, I'm making it like it's almost like a revision. So when you come back to college and have an option to refer the textbook, the Latchman textbook, you can refer the normal, the green color book, where you can have all this. So again, don't go in detail. We are just understanding superficially because the part of the first chapter. So it is not the chapter as a major chapter we are studying. It's a part. So as an examples, I want you guys to remember some of the things. We don't know in the M-Form level what type of question is expected. So safer side, you should have little additional information with examples. So chlorpromazine hydrochloride is the one which is photochemical degradation happens, the photolytic degradation happen, and it follows the zero order kinetics. Again, this decimization is another chemical change which can happen, which follows the first order kinetics. The change in the dextro and the Leo form of the drug, which can be identified by the optical rotation. Change in the optical rotation can be used to identify. Means analytical method also is important. How to identify this decimization has happened. So the external lever rotation. All this can be done with the help of that optical aspects. So I'm just winding up here. I'm very sorry. There was a lot of disturbance happening in between. So I need to stop in between. So that's about the kinetics. So I just stress upon what are the points you're supposed to like learn is the order of kinetics. Concentrate on zero order kinetics. What is its equation? Fine. Then the k value. Sorry, that is the k unit of the k. Okay, and the t half. These are three components. One is the k, its unit, and the next is t half of the zero order kinetics of the first order kinetics. Because zero order and first order, they are different from each other. But when you come to the first order and the second order, the k unit remains same. There is not much difference in that. But you need to remember the zero order, first order. What is the meaning of pseudo first order kinetics? And the example for all this, followed by the second order kinetics, example for the second order kinetics, and then comes the Arrhenius stability study. What is its equation and its applications and its limitations. Followed by that, what are the factors which can affect the stability of the drug? Overall picture like pH, ionic strength, or the acid base ingredients which are present in the preparation, all this. Okay, and some of the examples like I asked whatever I highlighted, examples specifically with respect to the particular reactions, which kinetics it follows, like oxidation follows the first order degradation process, ester hydrolysis follows the pseudo first order reaction. All this information you should have. So I'm just winding up. There's an exam allotted for me. I need to go with that. Okay then. So meet you day after tomorrow with the next subtopic of the same chapter.